kinds of problems does a logistics company have that can be solved with math and with data? Like, what kinds of expertise does your team need to have, and what kinds of projects are you doing?
The long and the short of it is that just imagine the food supply chain. So you have got a basically multi-millennial effort, the entire history of humanity, geared towards figuring out how to feed itself. And the modern incarnation of that is a whole bunch of pooled infrastructure, whereby almost no one that manufactures food is actually responsible for the handling and distribution all the way down to the consumer. What instead happens is people go through facilities like this. This is a rendering of a plant we operate in Charleston, South Carolina. We have these things everywhere. And if you add our competitors to this, it's basically close to food producing regions and it's close to population centers. So it is everywhere. And ultimately it's storage capacity. And basically you would not have heard of Lineage Logistics. You probably would not have heard of our competitors, but you would have heard of our customers, whereby this is 8 tons of Sabra hummus sitting on a dock in Richmond. We do all the blasting for Chick-fil-A. If you're gonna have a chicken sandwich, don't forget your 55-gallon drum of honey barbecue sauce. We handle most meat exports, or most refrigerated meat exports, out of US ports. We even receive deadliest catch. So this is a fishing trawler from the Bering Sea unloading at our facility at the Port of Seattle. And now, to give a long-winded answer to your question, you imagine the problems associated with this. The most important, arguably, part of cold storage is the cold. You accomplish that by moving and controlling the temperature of air. That is an exercise in physics. This is a CFD simulation that we made of a blast cell that a person on my team named Alex Zhang designed. You could call this AI, you could call this data science. It's actually applied physics, but whatever. It's a giant high dimensional gradient descent. And so if you know the mathematical methods to do AI ML, then you also know how to do stuff like this. You've got your kind of classical supply chain graph theory problems. So these are all networks, whereby food generally comes from, let's just say there's many fewer locations where food is coming from than locations where it's going. And so high in the supply chain, close to the manufacturers, the farmers, the CPG companies, is going to be relatively few sites, and then it's going to fractal out. It's going to go to regional distribution for shipments across entire states. And then from what this is showing is from those regional distribution centers, it's now going to the local distribution centers of the retailers. And so there's a time domain in which this is happening. You have to have sufficient frequency of shipments because this stuff is perishable. There's huge utilization complications, whereby you've got a 90,000 pound gross weight 18-wheeler tractor trailer. You're trying to utilize it. There's just all kinds of logistics complexities. We've even had, when you work in logistics, you have these just crazy conversations where this was us thinking about renting an entire freight train. And so we were trying to mine who was going in with meat from the Midwest into the Port of Long Beach, LA. So that we could see whether the volume justified actually like getting our own dedicated freight train. There's a whole bunch of warehouse design questions. And so, for instance, the rack on the left is probably default in the supply chain. The rack on the right is what we build using reasonably advanced stats and combinatoric mathematics, where we're trying to predict the distribution of pallet sizes. These things vary seasonally, they vary by market, but you use a bunch of fancy stats to figure out a reference distribution that's safe, and then you use a bunch of fancy computer science to assign different height objects to various rack columns, and then you go have a general contractor go build it for you.
So what you're saying is you solve a literal bin packing problem.
Yes, we actually physically bin pack physical systems. And then I think the kind of magnum opus, at least of the combinatorics and the statistics, is now the robotic applications in warehousing. With COVID, supply chain resiliency is frankly trying to depend less on the humans. There's certain huge environmental and energy benefits from building robotic warehouses. They can be physically taller, so you need less concrete, you need less refrigeration. And at least up until COVID, the labor market was really, really tight. And so as we're trying to schlep more food through the same assets, more food to feed a growing population, we like literally could not find the labor that we needed. And then lastly, I think for your purposes, I'll touch on probably what I think is the most interesting area of kind of classical AI ML, which is vision. This is a device that we developed actually with a startup to identify labels on pallets. One of the main manual processes in the supply chain is saying, okay, this stuff is unloaded from a truck. What is it? How many cases are there? Are the day codes square? Is this expired? Is this damaged? And these are kind of classical vision applications. But then also we're using vision, mainly low compute, low profile, low power innovations from quadcopter drones in order to localize forklifts within facilities. And so you put little
You're flying drones through the warehouse and repositioning forklifts based on what you see?
No, so we took the compute package off of a drone that could fly around the warehouse and then just duct taped it to a forklift. And that tells us all kinds of interesting things. So
that's great.
I'll stop there.
I love that.
That's kind of a high level overview of our problem set.
Awesome.